Hello. For this video, instead, I want to talk about one of the most beautiful concepts I've seen in computer architecture, and this thing is called out of order execution. It's also called dynamic scheduling. So so again, let's start with the motivation and see the problem setup and why is the case we need such thing. Um, so if we go back to the just the basic setup, again, we have this RISC-V 32i, and the 32i is like the basic of the basic form. And with the 5-stage pipeline, we basically have FD, E, W, MW. So that's the basic pipeline that we're gonna see. And then here we're gonna highlight some stuff that is relevant. So first of all, that we just had a bit of review about the data dependency issue. So let's talk about data dependency somewhere here. Okay, I'll put it here. So what's data dependency? Let's go through it again. So there's something called the rule. It's called read after write. Read after write. And what's read after write? It basically just means that you maybe have R1 and then you're updating by R2 plus R3. And the next cycle you're going to use R1 plus R4 and update it to R5. And the idea of this data dependency is basically you have a read. This is the read operation, and immediately follow a write operation. And why is that an issue here? So in single cycle, there's never any data dependency issue, but somehow in the pipelining stages, we have two things we have to consider. There's two kinds of hazards that we know. First thing is data dependency. So it's data dependency. And second is called the control dependency. And just to summarize what actually happened before was that remember how we used the so if we actually try to summarize our strategy to go against the data dependency and control dependency is data dependency, yeah, surely we can do something. So we can do something about data dependency, but the control. Remember that we talked about the branch prediction last time. So when we talked about branch prediction last time, it basically is trying to resolve this control dependency, because last time we said you need the early and you need to go through the early and main to sort of resolve what sort of branch address and also whether to jump or not, to know this to try to solve this bubble issue. So yeah, so control dependency is pretty much done by prediction, and it's really not so you pretty much have to guess. Otherwise, you can't really do anything about it except just having a prediction, isn't it? And then meanwhile, for data dependency, it's possible to do by what's being called a dynamic scheduling. It's called I'm gonna call scheduling. And then I'm gonna talk about scheduling, and then but this we haven't talked about. But then we also talk about what's being called the data dependent, like data forwarding or store flush, that sort of thing. Yeah, flush. You'll have a flush required. You will have a flush required under low word exception. Sorry. Yep. So pretty much this thing we saw about, this is the store. This is the store for low word, and low word is the only exception. I'm gonna go through that again. And data forwarding is pretty much all other exceptions, and this can be solved. But then how come? So this is pretty much summarized in our course so far. So that we have data forwarding, that's solving everything else, and then the store and flush will pretty much just be solving the low word issue. But then the question comes is, oh, why do we ever need a scheduling? Because as you can see, if I only have to store for the load instruction, the penalty seems really small, and the bubble is really small as well. So yeah, let's keep that in mind. For 32i, pretty much this thing is enough already. So the scheduling, how come I still need it? Let's keep that question for a bit. So yeah, pretty much you have to read after write in here for the road dependency, and let's review on actually what happens. So over here you have your register file, reg file, and then somewhere here you have your ALE, and then over here you have your mem, and this is your write back, where there is like multiple mocks, and then you feed it back to your register file. So what happened was when do I need the data? So I need it here. And when does the results, maybe some, okay, so let's try to distinguish some of the cases. So let's go back to RISC 5 and let's take a look at all the instruction set. So if I were to look at what I need, I can just go through, okay, say R type and I type for all the ALU instructions. So it's coming from the add and add immediate to set less than and set less than immediate. Those things, I can immediately have my results in my ALU. So this is ready for R and I type. But except I type, I mean sort of a narrower I type, which is just only the ALU type of ALU I type, that sort of thing. And then low word is, we talk about that section. Store byte and half byte. We can only fetch our results by having them met here. This is ready. Jump and link is pretty much print instruction, so we don't really have to know about it. We don't really have to know about it just yet. Yeah, and the rest should be all right. So let's just talk about the majority of the stuff that are required. Which is, if you have your register file here and an ALU file and memory file, and then also your write back, what happened was you're gonna end up finding, let's just say this. Let's just say keep the rest. For instance, the because the branch instruction doesn't really modify any register file, but then for your jump and link register, load up immediate and load up the immediate to PC. They are all tempering the RD with PC pass 4 or immediate or PC pass immediate. So yeah, I'm just gonna put them all in the write back stage. So this is pretty much S type, and this is just I and I type, and this is just U type. Yeah, let's just say that. Let's just say that, or some of the I type. Let's just say that. So what happens is you can see that the idea over here is that if I have a read after write dependency issue, when I have F D E M W, F D E M W, F D E M W, that sort of thing. So what happened was set that the first scenario, which is all the R and I type. So we try to solve this. So set that if I have R and I type in the first instruction, and the second one is no matter what, and I pretty much need my register at decode stage. But then my as you can see, my result is sort of ready in the execution stage. We sort of say this idea is data forwarding. So if there's no data forwarding, what happens is you can only update it through the write, and this is when your register get updated. But then you already want your register file to be here already. So that's bad because you're not reading the old value instead of the new value. So yeah, that's the issue. And the problem setup is pretty much what taught in the textbook of Harris and Harris, which is saying, okay, I have execution stage, and over here I have the old value, and this is new value. So what happened was over here we can pretty much just forward the value to be saying, okay, between here the pipeline register, I can just forward it like that. So my execution stage, once that's ready, instead of getting the old value here, I can pretty much just do the mocks, and then just instead just use a mocks and then update it through the register file. But then you typically, if you go to here, you probably don't see that setup quite often. The reason for that is because instead of data forwarding, what happened was instead of forwarding to the end of the stage, instead of forwarding into the end of the stage where I mentioned before, where you have the ALU, instead what they do is, because I think this is probably to do with some sort of critical path issue, because you pretty much have to go through the entire thing and then go back and then do the mocks again and go back to register. Maybe that's the critical path will be too long or something. So instead what happened was, you can see that what they do is going here, fetch this result and go to the end. So instead of like end to end, instead what they do is they just put it into the result. While this is still the old value, while this thing is still the old value, like the previous value that hasn't been updated. Here, before they pass into each execution unit, I just simply pass that. Yeah, so that's it. That's it. So this is what you call the mem to exe forwarding. That's one type of forwarding. So m to exe, m to ex forwarding. Yep. So that's good. So yeah, I is resolved because as long as I have execution before, because data fetching from register file, it doesn't really do anything, isn't it? So as you can see, there's no operation that has been done. So as long as I just simply just like, I don't know, hijacked this signal and it's like, oh, and is hijacked a good word? I mean, like intercept the, and it's just like, oh, get rid of it, and instead I want to change it by using a mux. Isn't that kind of nice? So yeah, so that's basically one type of setup. But then the idea is, what happens if the first instruction is not I-type? It probably will be S-type. So if it's S-type, then the problem arises that I can only got the ready one in M-type, is it? So what happens instead? Oh, actually, hang on. Let's take a look at the S-type again. So for S-type, you pretty much have to wait until the end of the memory. You pretty much have to wait until the end of the memory. Yep. So again, it will be ready in the memory stage, but then we said that we have to, instead of going through from the end of the memory, instead we want to go through the earliest of the write back cycle. So as you can see, there's another pathway that goes through here, which is just this thing here. Okay, so this is pretty much the support for the store word, because if I have the write back stage, right? If I'm ready in the here, but now the question is, I can only go through in the write back stage in here, so I'm ready only here. So this is the support if you have S-type. So I guess, okay, this is the part where I actually got a little bit confused. Is I guess that if you need this M signal before your E signal, probably you need a store probably here. You probably need a store after your store word, isn't it? Because you can't really do anything about it here, so you sort of had to insert a bubble. Okay, interesting. I actually thought that you only need that for store word. No, I guess that you probably have to. Let me just clear this up later on. Maybe in a comment or something. This is really interesting. But anyway, there's a pathway between the W to, so there is another pathway between WB to EX. As you can see, this is actually happening between here. So one of them is fetched from the write back stage, and the other one is fetched by the memory stage. Yeah, so that's pretty much it. So I guess that you still need a bubble around here. Then what about the write back? The rest. So if you have a write back, which is the U type and I type at the write back stage, then you pretty much only have the ready this is kind of one of the reasons why I keep liking to talk and then upload on YouTube, because it runs through my logic again as well. So I kind of recommend that if you any concept that you want to sort of review about, it's really good to have this sort of setup and then talk to like talk through the video on something like that. Imagine you're teaching a friend, and then eventually you're gonna find out there's probably something wrong in your logic, and you ended up can fix it. It's good. Yeah. So the for the U tab and I tab, I pretty much only I don't know said that I only know the results in the write back stage. The write back stage actually was really interesting. Is that there is the setup is kind of like this. Oh, sorry, decode stage. So in Harris and Harris book, we kind of established that over here, it said that if I have a data dependency here between here and here, then the idea is I'm gonna have to update the first, like I can update in the negative edge and then positive edge. So every register is updated in a negative cycle, and then every register is read in the positive half cycles. As you can see, this is why the shading here. So if you've done that, then pretty much there is a once you fed it back here, and then it updated in the first half cycle, and then it read in the second half cycle, then you pretty much resolve the issue by having a fetch state. It sort of just looks like that. So there's another data forwarding here. So yeah, I thought I didn't really explain the data forwarding that well, because essentially there's multiple possibilities. Like, okay, if I have to so there is pretty much just forwarding here, and then there's probably another forwarding in here, but then that doesn't resolve the issue. Say if you need this, what happened? So yeah, if you need to write back to memory, that's one possibility, but then you probably just need to use the store. So if you why is that? Because your execution stage pretty much do the computation. Just let me think about the store again. Think about the store again. Because normally after the execution stage will be like you actually do a computation. So forwarding after that wouldn't be any helpful, is it? Except some type of other thing that you probably didn't do any computation. But like majority of the time you want to forward before the execution stage. So I guess that if you have a data forward path between read back and memory, it doesn't really help, isn't it? So in that case, what you do is probably you can only do it by store and flush. So I guess this probably have to use the store word as well. Maybe I'm gonna check again, because store, right? If you use the store word, then the store will only be readily available in here. So you can only have the data forwarding path here, which means that if this is requiring what you need in a store word, then it doesn't really help. Yeah, anyway, so that's the problem setup. And you can see that there's some cases that I couldn't solve by having the store. So probably the memory operation, which is the lower and store, will require a store. Yep. So that's pretty much the setup. And how much time have I taken? Oh my god, Jesus Christ. Yeah. Okay. So that's just a bit of a review. But then the question actually comes to, okay, when do I actually need a scheduler? Okay. So if you actually look at the M extension, so 32I, maybe M as well, or maybe you look at the floating point, which is the, I don't know, F unit or D unit, maybe F unit or something like that. So imagine the setup as, because you remember how when you have the multiplier is it's a serial adder. No, it's not serial adder, sorry. It's a ripple carry adder, but then in a crazy way, because you basically need a large adder, isn't it? Like your hardware is, you either have to use a very complex when you use it, you either have to use a very long hardware, which costs a lot of time, or you're going to use a pipelined stage for all the hardware. So imagine if your plus take 1 cycle, then your multiplication probably take, I don't know, 4 cycles or something, because of your internal hardware. And then the reason for that, it hasn't really disclosed yet, but just think about the hardware itself. Is just because for addition I just need to simply add by one time. But then if you take a look at what's actually multiplication, so like a1, sorry, a4, no, a3, a3, a2, a1, a0, b3, b2, b1, b0, b0, and you pretty much have to, no, sorry, this is b2. So you pretty much have to have the like a3, b0, a2, b0, a1, b0, a0, b0, up to a3, b3, a2, b3, a1, b3, so that sort of thing. And you're adding, like, you have two things adding together, and then adding the next, and then adding the next. So in that case, you can see that the adding operation is kind of expensive here. Not to mention, if you have 32 bits, you can see that now the question becomes quite crazy. So yeah, the ripple carrier adder becomes one of the issue, because the propagation delay will be quite significant. Even if you have one level, now you have like probably 32 level of delay. So instead, what happened was, typical way of doing that is pretty much having a pipeline for all the complicated stuff, such as the division. Division maybe take I don't know, majority of the time. Let's see what the recif have to say. As you can see, it has. Remember how I said that last time? You have a instruction queue here, and where you have like maybe a different execution unit where it does other stuff. So this is pretty much the standardized way of doing stuff. And then I'm going to introduce another paper called the microarchitecture for superscalar processor. And this is actually really cool because as you can see, what happened was, just take a look at this setup here, which is having a floating point unit and also the integer instruction buffer. So this is basically just saying, as you can see, I'm basically separate a whole machine into two different parts, two different register files, including the floating point and also the integer point. And yeah, so integer register file and then a floating point register file, and then it also separated into two different functional units. Why is that? Because this thing typically take much more longer in terms of the cycle, and this thing over here probably take less cycle. Yeah, so that's the setup. And here comes the actual punchline for what's going to happen if you introduce this varying pipeline stages. So I'm going to call this varying length of the pipeline. So it could be the case that where your maybe your 32I instruction will be F D E W F E M W. It could be the case like that, right? And there's nothing. It was just a basic case. But then if you go for maybe 32M, maybe you make a decision and you want to do an internal pipeline between all your execution for multiplication or division, or that maybe you want to set up as a 4-cycle execution, so that it doesn't really dictate your so that your multiplication unit doesn't really dictate your pipeline critical path. Yeah, because remember the critical path is like in specific stage, you want a critical path that's the longer stage, and of course if you put the multi-cycle unit inside the execution unit, it's going to dictate the whole stage, and perhaps if it's too long, it's going to dictate the whole clock frequency as well. That's bad. So instead, you probably want to have an internal pipeline between them. So the setup probably now looks like, yeah, it goes through for my 32I instruction, but maybe I'll put next to ALU maybe another moldiv M, and then probably have the internal pipeline just go through a few cycles and then go to the memory, something like that probably. But instead, you probably have to remember that if you're doing floating point, then you definitely have to do a separate one. But now if you're just talking about M extension, then you can still fetch it from the same register file and then just let a pipeline in, and maybe a multiplexer here, some stuff. Yep. So now there's an issue, and the issue comes again, which is the data, which is again and again data for like dependency issue. So the motivation actually comes in this. So said that if I have a very long instruction, and said that okay, so said that if I just have R1 equal R2 multiplied by R3, so we know that it has to be readily available in here. Maybe I'll just make the case a bit more dramatic by introducing E5 and E6, and then memory, and then write back. Okay, so you're still going to use the data forwarding issue. Say it's data forwarding, and then we're going to say that the next instruction is probably like I don't know, R5 equal R1 plus R4. So we're back to the 32 instruction. So it's going to be R, D, E, M, W. Okay, so the idea is, and then you have the rest of the code, and pretty much just FD, sort of thing going on. So there's like a code section here, which is like for the rest of the code. But then what happened was, here comes the bad thing when you introduce this varying length pipeline, which is your result is readily available in here, which is equivalently in pipeline here, like we said. Okay, so if I'm ready in this stage, I can pipeline. I can data forwarding. This is ready, but then I need that for like ages ago, isn't it? So that means how many bubbles do I need to insert? Like 1, 2, 3, 4, 5, and I can have my D here. and 6 maybe. So yeah, as you can see, I pretty much just have to move every single thing. So instead, I pretty much have to do everything like then I have to do something like this. Oh, then I have to do something like this, and that's really, really expensive, isn't it? Because like if I just move one cycle, if I just move one instruction, that's fine. But now I'm moving the entire block of thing, isn't it? Because I can't start anything after. I can start anything before that, and then the rest of the code I have to move accordingly as well. So that comes with a very, very expensive idea. Sorry, that comes with a very, very expensive bubbles over here. So that's very bad. And we're trying to solve this. And the key idea for out of order execution, the motivation comes in for the punchline, the long instruction block the rest of the code. Yeah. So imagine this. Maybe I have the next instruction. So yeah, for sure, my R1 plus R4 definitely have to wait for my because there's a true dependency between here is called the rule after write. So I definitely have to write no matter what. So yeah, they definitely have to be executing here. But what if instead of moving the rest accordingly, what if I just move in the front? So instead, I know that. So here comes the actual idea. If the next one is probably something like R2 equal R4 plus R6, there's no dependency here, just so you know. But we're gonna introduce later. It's actually there is another dependency, but then R2 plus R4. Yeah, so it doesn't really need any update for the data. There's no data dependency, which is fine. So here comes the idea of data scheduling. So I know that my D for my for this instruction, I'm just gonna put 2, 3, 4. So I know that for 2, my decoder stage has to be here. It has to be in this time step. So what happens if I just make it a bit later? So instead, I'll just execute my maybe R3 first. Oh, sorry, wait. Sorry. This one's 1. This one's 2. This one's 3. So what happens if I just execute the third here? What happens if I just, I don't know, if I just execute my 3 first? Wouldn't that be kind of nice? So the idea is probably, I don't know, I'll still fetch my 2. And then maybe at the decode state, I end up finding, okay, yeah, I can't do anything about it. So let me just wait here and let the F3 go on. And then you can just do the execution. Wait. So if I just let the 3 keep going on, and then while my R2 just keep waiting, this is essentially, if I can just, okay, sorry. My idea was, not my idea. I mean, the idea is, if you just swap this around, so I execute the 2 later, and then I can just let the independent instruction, such as this, which doesn't have any data dependency issue, so it runs first. If I let it run first, isn't that kind of nice? Because there's no data dependency, I can run everything and nothing will go wrong. So that's pretty much what I call out of order execution. So as the name suggests, we're executing something out of order. So there's actually something really interesting is that there's basically 2 types of thing. So your fetching will be in order. And over here, imagine that you do some sort of dynamic scheduling. And then after that, you're gonna run through the whole thing out of order. So I'm gonna use out of order here. And then in the end, I retire in order. So in that case, you sort of have this illusion of basically putting everything in order and in order. But then when I do the execution, it's actually out of order. Let me show you one of the example for actually this example will be quite tedious, I think. Yeah, this is the case when you have the register renaming. Yeah, this is gonna be taking quite long for this video, I think. So yeah, the basic setup is just like this: in order, out of order, and then in order retirement. Let's just probably conclude this video by saying this is a reorder. There's a let's probably take a look at here before we end this, and then we're going to talk about in the next video about how to do the register renaming and stuff. So as you can see over here, we have the dispatch. So this is what you call the so here over here, everything here so far is pretty much just in order fetch. But then over here is when you start to dynamically scheduled your instructions, saying, okay, I can sense that there's a dependency here, so I'm just going to let it hold, and then the rest of the instruction I'll keep letting you run first, and then maybe I'll execute this later on. So this is pretty much a dispatch. And then there's something called the renaming, and the renaming actually comes in with a different hazard, but really important when it comes to varying length hazard. There's some issue with it, and so we have to do the renaming. And then over here we have the reorder and commit. It's pretty much is, as you can see, when I finish everything, I just pass it in, and when I finish everything, I pass it in, and then I will say, okay, done. So so that's basically the retirement part. So like, okay, I've done everything, and then I just retire, and then put every sort of update back to the architectural state. So as you can see, back to the register file or back in the memory interface. Is it? Wait, does it have the memory interface connection here? Probably not. Yeah, okay, sorry. The memory interface is probably done by because we know that we have FDEMX right back. So pretty much the right back stage is doing this thing, and memory stage has been dealt with in the middle. But I think memory has a lot of dependency issue again as well. So yeah, this thing become quite crazy. But this is one of the most beautiful thing ever, invention ever. It's called a Tomasello algorithm, and it's been invented for a while, and then now every computer, basically every single computer, modern computer, uses this strategy. So yeah, hopefully there's maybe I should pull up another better example, maybe root DDCA. Maybe I should maybe I should take a look. This is one of my favorite calls. If you go to lecture 15, there's lecture 14. So as you can see, pretty much just everything like this. So again, that's a setup for having an integer add and multiple, and maybe the floating point multiple. Then also you have a cache miss. Then there is a what happens if you have a cache miss? Then there is like a multi-cycle waiting for your memory, isn't it? So yeah, this is the in-order pipeline, and pretty much what's happening here is long latency instruction stores the pipeline, and impedance instruction cannot enter. So the idea is what happens if I so as you can see, the low word and the low data and also the multiplication block the rest. And while the rest of your blue code, which is the add, it doesn't really rely on any of the previous code. So what happens if I can just schedule them first? So the first add stores the whole pipeline, isn't it? So if I can just let the later independent instruction do the dispatch first, isn't that kind of nice? So the idea is just out of order, and it's called the dynamic scheduling. So as you can see, pretty much what happened was when my first instruction is stored, so what happened was, remember how there is a store happening? The rest of them has to be stored. So remember how we moved the entire window. We moved the entire code block into when this is readily available. And there's pretty much a window between them, which is bad. So what happened was, if you have the out of order try to solve this issue, is that I only have to wait for this first one. But while I just said that, okay, I'm going to detect whether there's any dependency here, and I'm just executing the rest. Sorry. And while try to keep in mind that we are still doing the in order retirement, which is see how your right back stage are also everything in order. So my out of order, as you can see, how come there's a window is because yeah, I can write back at this stage, but then I still need to in order retirement for this. I'm going to talk about a little bit more about in order retirement in a bit, and why is that the case? Why do we need such thing? So you can see that actually there's improvement by having just, I don't know, within this 5 cycle, you can see that there's quite a significant improvement here. Yeah, So I kind of so if you're interested, I think there's a paper here, and then yeah. So if you want to read the efficient, this is by Thomas Ulum stuff, and then that's the schedule, and then also the reorder. So pretty much just two hop, and as you can see, that's the paper from same thing, and this is the paper from the this is pretty much a paper from Thomas Ulum. Yeah. So that's the idea. The problem setup is I pretty much want to have this reschedule. So saying that okay, over here maybe some of them will run first. So I'll just detect some dependency here, and then run it, and then in order retirement. So yeah. So always if you're confused, then just maybe take a look here and compare. Okay, this is pretty much the decode stage, and then the execution stage. It might be like running out of order, such as here my execution stage runs before my second one, yeah, or my fourth run before my second execution, which is so weird. How is that not breaking anything? How is that not breaking the von Neumann sequential model? Then also why is it the case that we always need the in order retirement? Okay, so I'm gonna end here and then talk about a little bit more in the next one.